It's really great seeing how crowded this is after how quiet it was last year. It's my pleasure to introduce Professor Andrea Young of UCSB. So Andrea did his PhD at Columbia in Philip Kim's group, where he was lucky to be there with his friend and colleague Corey Dean, doing a lot of the seminal experiments in the physics of graphene. For some of that, he was awarded the New Horizons Prize recently for this technique that they developed together for building really clean, pristine graphene materials, which has really been the basis for this huge explosion in the field of using graphene, not just as a system to study the uncorrelated physics of the Dirac equation, but now lots of interesting correlated states like the fractional quantum Hall effect, and more recently, magic angle graphene. He then did his postdoc at MIT as a Pappalardo Fellow, and since has been at UCSB, where his work was awarded a Packard Fellowship, Macmillan Prize, New Horizons Award, etc. So it's my pleasure to have him here to talk about a lot of his recent exciting work in the physics of magic angle graphene and other interacting effects. So thanks, Andrea.
Thanks, Mike, for that nice introduction. And thanks all of you for coming out to hear about it. So the talk I'm going to give today is about orbital magnetism in graphene heterostructures. And just as a disclaimer, this is not going to be in any way a historical presentation of this material, but just try to give a sort of coherent story. So apologies if things are not cited in order and so on. So to motivate this a little bit, right, this talk is really about different knobs that you can get to control magnetism in graphene and related systems. And there are kind of two, general thrusts for why this is interesting. The first is just magnetism as a quantum mechanical and correlated phenomenon, which, besides its sort of basic questions of like what is required to give you a magnet, magnets of various kinds are also the foundation for understanding a variety of exotic phases of matter, including unconventional superconductors, various types of topological states, quantum spin liquids, and so on. So from the point of view of fundamental physics, one would like to understand and have new experimental platforms for probing magnetism, because it's just, at the theoretical level, a generic platform for realizing lots of quantum many-body states. There's also an angle to this, which is that of magnetic technology. So, magnets are obviously important in everything from electric motors to magnetic memories. But one of the sort of upshots, which I'll talk about at the very end of this, is that, by studying magnets in these new types of situations, we can try to gain, electronics-like control of magnetic states. So, the same way that in a transistor you can turn on and off electrical currents, you'd like to be able to do that with to magnetic states with electric fields, and that's not entirely obvious how one would do that, and it turns out that's possible. So that'll be sort of the punchline in some ways of the talk. Okay, so but let's start at the very beginning with kind of a brief history of magnetism. So the first reports of magnetism, as far as I've been able to find scouring Wikipedia, go back to Thales of Miletus in the 6th century BC, who noted the attraction of iron by magnetite, a mineral that you can find naturally occurring. And so that was a good experiment, right? He noticed something important, but he came to a wrong conclusion, which is that matter must actually be alive. And our theories of magnetism have improved since then. Notably, Niels Bohr in his PhD thesis actually proved that the free energy was independent of the vector potential classically. So magnetism is forbidden classically, and yet it moves, right? You have magnets. So that was one of the important things in the early days of quantum theory. So it's not a classical effect, it's a quantum mechanical effect. But there's another sense in which our experiments on magnetism haven't actually evolved all that much since the time of Thales, in that all the magnets that we know about basically rely on spin orbit coupling. And some of what I'll show you today is kind of some degree a different type of magnet that doesn't rely on it. So to give a basic introduction to the origin of magnetism, magnetism comes from the combination of repulsive Coulomb interactions and Fermi statistics. So one simple picture where you can see this is in, this is a problem from Landau and Lifshitz quantum mechanics textbook, actually. If you have a double finite square well and you ask what are the energy levels of putting two particles in these square wells that are interacting, meaning there's some amount of Coulomb repulsion, even when they're far separated, there's a little bit of overlap. And you can go ahead and write down two different wave functions. There's a symmetric combination of the ground state orbital wave functions in the two wells and an antisymmetric combination in the two wells. And then you can go ahead and calculate for these two states the Coulomb energy that comes from the repulsion of these electrons with each other. And if you do that, you'll find that in fact they don't have the same energy. There's a difference between them, which favors in this case the antisymmetric orbital state. Now, if these are electrons, they have Fermi statistics. That means the overall wave function has to be antisymmetric, which means that the spin wave function has to be symmetric. And that's basically the nature of that's exchange. That's the origin of ferromagnetism, is that there's this energy splitting that comes from Coulomb repulsion combined with Fermi statistics. Another way to think about this is that if electrons are repulsive, then if you have a state where they are their orbital wave function has to be antisymmetric, then they can't possibly overlap, right? Which means that that state will minimize repulsion compared to one where they can overlap. Okay, so then you can think about, that difference is going to induce essentially a coupling between the spins in this of the electrons, which is just that energy difference. And this then applies to, electrons on a lattice or electrons in a metal, right? And if you think about this Hamiltonian, this has a phase transition in 3 dimensions, and you have some ordered state, for example, one that is symmetric would be one where all the spins point in the same direction, and that's just a ferromagnetic state. So this state has a large magnetic moment. It breaks time reversal symmetry, and we'll have a 1 quantum of spin per site. Now there are of course like some subtleties, and so for example, in 2 dimensions you have the Mermin-Wagner theorem. You don't expect necessarily to have long-range order. So how do you have magnets in 2 dimensions or in materials that are very layered where they're effectively 2-dimensional? And it turns out that this gets resolved if you have some anisotropy. So if you have an Ising model, something where the spins are constrained to point out of the plane only, then it's perfectly fine to have a phase transition. You don't have a continuous symmetry you have to break. You just have a discrete symmetry, so the spins can point up or down. You just have to choose one of the two. And that's allowed at finite temperature, as shown by Ansager in 2 dimensions. And the way that you induce this anisotropy generally is by spin-orbit coupling. Most materials have some amount of spin-orbit coupling. Some of them have a lot of spin-orbit coupling. And that spin-orbit coupling combined with the strong electric fields inside a crystal generate some anisotropy for the spins, which then makes them, let's say, point in or out of the plane. And that's basically what happens in magnetite, right? On the other hand, this is, what is spin-orbit coupling, right? It's a relativistic correction to atomic physics, right? It's intrinsically relatively weak, but it gets strong enough as you go to larger Z, right? And it goes with some high power of Z cubed. And so what are the ingredients that you want then to have a ferromagnet? You want to have ideally heavy atoms are involved. You want the orbitals to be relatively localized, right? To make that exchange interaction relatively strong and so on. Those are and if you look at most magnets, they will have some, local moments and strong, at least reasonably strong spin-orbit coupling. Okay, so from that point of view, graphene is an extremely unlikely place to look for magnetism. So first of all, it's extremely 2-dimensional. So you certainly need to worry about, the absence of long-range order in 2 dimensions, for example. The wave functions are very delocalized. So just to remind the or to tell you who are not working in condensed matter, for example, almost everybody I think who now takes a condensed matter class probably solves the non-interacting band structure of graphene but the low energy effective theory that describes the electrons hopping on this bipartite honeycomb lattice is that of Dirac electrons. So there's a Brillouin zone, which has 2 inequivalent corners, and all of the low energy states, the states that you access in a transport experiment, for example, occur at the corners of this Brillouin zone, and they're described by a linear dispersion, just like massless electrons would be, where the sublattice and the phase of the electron wave packets on the different sublattice kind of distinguishes these two valleys, which sort of play the role of a pseudo spin in the low energy physics. It's all made of carbon. So you have these very light elements and effectively no spin orbit coupling to speak of. So really, all of the things I've told you about what makes a good ferromagnet, graphene does not meet any of them in effect, right? No spin orbit coupling, extremely delocalized electrons, and so on. So, not looking particularly good. Okay, on the other hand, there is this new degree of freedom, which is the valley itself. So although the spin has no spin orbit coupling, there are actually different, these different valleys which behave like a spin in the sense that they they endow the electron wave packets, which might be very large on the scale of the lattice, with a microscopic degree of freedom that can allow you to distinguish two different electrons, can turn out to play precisely the role of the spin. And basically what this talk is going to be about is how to construct magnets based on this valley degree of freedom. And as a result, all the games that you can play, given that you now have a completely orbital moment. Because in a condensed matter physics experiment, if you want to manipulate spins, there's sort of only so much you can do. You can apply magnetic fields and turn them up and down. But orbitals are much easier to manipulate, because as you change the carrier density or you tune the properties of your material, you can completely change the band wave functions. And it turns out that all of the magnetic properties will be strongly dependent on those band wave functions in some way that can turn out to be useful. Okay, so just maybe I'll just go ahead and get started on how do we turn graphene magnetic, right? And again, I'll go through these things in a non-historical order. Okay, so one way to think about magnetism in a system like graphene in a metal is through the Stoner criterion. So as I told you before, you gain a little bit of Coulomb energy when you when you allow your electrons to polarize into, let's say, a spin, but would be equivalently true for any valid, for any other microscopic quantum number. On the other hand, in a solid, you have a finite bandwidth. So if you now have your electrons all occupy the same spin degree of freedom, then you're going to necessarily, instead of doubly occupying every state that's available in your band, you're going to have to singly occupy them. And that's going to cost you some energy in the form of basically the bandwidth. And so you can think about, an energy band. What I'm plotting here is the density of states for some generic band in a solid, right? And the way that band structure works is that if you have some solid and you just solve the non-interacting Schrodinger equation for that solid, you'll find that there's some range of energies where you have states, and then some range of energies in between where you don't have states, and these are the band gaps. So if you have a partially filled band, you have some density of states within that partially filled band, and if you're going to singly occupy this whole band, it's going to cost you extra energy compared to doubly occupying every state, in which case, let's say you would half fill it. So there's a competition between this bandwidth, which is something that is tuned at the level of how you make your material, and the strength of the Coulomb interaction, which is tuned by how close the electrons are and the overlap between their wave functions. And this results in something called the Stoner criterion, which basically says if you have inverse density of states, which is really a way of saying if this bandwidth is smaller than the strength of those Coulomb interactions, then ferromagnetism will generally be favorable. And of course, graphene has a very low density of states, because if you think about linearly dispersing particles in 2 dimensions, they actually have a density of states that vanishes near low energy. So again, not looking very good for magnetism. Okay, so here's an illustration of that. So if you have monolayer graphene, you end up with a density of states that goes like square root of n because of this linear dispersion. It doesn't work very well. Okay, so most of the physics I'm going to tell you about today comes from the basic fact that this can all change as soon as you have more than one layer that is coupled to each other. Okay, so the simplest example of this is to simply take, instead of 1 layer of graphite, to take 2 layers of graphite. Okay, and if you do that, you just study bilayer graphene. This is just, again, like the conventional structure that you would get inside a piece of graphite. There's a strong interlayer coupling that happens at the atoms that are right on top of each other. And if you go ahead and figure out the electronic structure near these K points for a graphene bilayer, what you find is that your density of states changed a lot. It went from being linear in energy and as a result, square root of density, to a constant, which is an improvement. It's not great. If this constant were big enough, it'd be good. But at any rate, it's an improvement, right? You've gone from essentially vanishing density of states at charge neutrality to a constant finite density of states at charge neutrality. So it turns out you can do better if you now take that graphene bilayer and apply an electric field across it. What happens then is that actually this band structure changes. You open up an energy gap at charge neutrality. And what's sort of remarkable is that that energy gap at charge neutrality is a little bit unusual because normally in semiconductors, you have some minimum, and that minimum is quadratic, and that gives you a constant density of states in 2 dimensions. But here you started with a quadratic minimum because of the details of the band structure of this material. And when you apply an electric field, you actually end up with a band structure that is a quartic minimum in energy. It goes basically like p to the 4th. And if you think about p to the 4th dispersion in 2 dimensions, it turns out you get a density of states that actually diverges as you go to low density. So now it seems like the Stoner criterion should be basically automatically fulfilled for some sufficiently low density because the density of states is basically diverging as you get to the band edge. Just as a quadratic dispersion in 1 dimension has also an exploding density of states. So this idea, it should be arbitrarily favorable at very low densities to go ahead and put all your electrons basically into 1 spin state or 1 valley state. You're always going to win, at least in this simple model. Of course, reality is a little bit more complicated, and I'll show you that a little bit in a little bit. But it turns out this is kind of an instance of a larger class of types of graphite, which are rhombohedral graphite. So the normal structure of graphite, you probably learned in like high school chemistry, you have a sheet of graphene and then you have another sheet of graphene that's lined up so that one of the atoms is on top of an atom in the first layer and the other one is in the middle of the hexagon. And the structure of graphite, the sort of most graphite, the third layer goes back exactly aligned with the first layer. But there's a second way you could do it, which is to basically put one of the atoms in the middle of the hexagon that doesn't have an atom in it. That's called the rhombohedral stacking order. And it's very close in energy. It's something that's, if you have a chunk of graphite, it'll have pretty large pieces of it that are rhombohedral, even though, there will be lots of rhombohedral domains inside it. Even though it's not the ground state, it's pretty close in energy and it's easy enough to find them. So, so it turns out that crystal structure is sort of more of the same, except it has an even bigger divergence in density of states. And if you keep stacking up rhombohedral layers, they get bigger and bigger, this density of states, at least inside a relatively simple model. So this was a kind of promising place to look for ferromagnetic physics and try to understand this relatively well. So so how do we, so the experiments I'm going to tell you about are all made more or less in the same way. We make devices where we have 1 or 2 or 3 or however many layers of graphene that are the thing that we want to study. But we also want to be able to control their density, so how many electrons are in them, and we want to be able to control this electric field. So to do that, we need to basically add gates to them, just like in a field effect transistor. You need a gate that you can apply an electric field, usually on the top and on the bottom. And by controlling those, you can control the electric field through it and also the total density just by charging that capacitor. So to make these, we start from Scotch tape. And we, just like I think probably many people in this room have done this experiment. I'm sure if you come from Feng's group or Mike Cromie's group or any number of other groups, at this point, this is super common, right? But you start by exfoliating these layers out of a bulk and they sit on a substrate. And then you need to make these stacks of graphene, but also dielectric materials. And the way you do that is you start with your substrate that has a 2D material on top, and then you use some kind of polymer film. And this is sort of where the art of this goes, is into designing that polymer film and the conditions where you can squeeze it down onto your layer and then pick it back up. And now you have this layer on this polymer film that you can move around. And then you can repeat that over and over again. And the key thing is that these van der Waals interfaces, especially between graphene and boron nitride and various types of transition metal chalcogenides, are very sticky. So they will stick to each other better than they stick to anything else. And you can actually make, it turns out, atomically sharp, very clean interfaces between these different materials and build up 2-dimensional heterostructures that way, more or less at will. So this is what it looks like, just to give an example. That's a piece of boron nitride. And what you're seeing here is Newton rings from laminating this polymer on top. And then as you withdraw, you see them coming. And then at some point it pops off the surface, I think in the next frame. There we go, right? So that's how you do it. And then you can iterate this process over and over again and build up structures like this one, which was a little misguided in its complexity as it turned out, but you can certainly do this over and over again and make structures that have many layers of graphene. We actually, this turns out to be very good, right? For reasons that are maybe obvious to those of you in condensed matter experiment. Everything here is basically a van der Waals crystal. There's no interfaces that have any dangling bonds. Hexagonal boron nitride has the same crystal structure as graphene, so it's just planes of boron and nitrogen rather than planes of carbon and carbon. And graphite is, of course, the same crystal structure as graphene. You can use that for all of your gates, and you can make these multi-layer structures, up to some relatively complex level here. This one has, 12 or 13 layers. Now, what's kind of remarkable about this is that it really does realize an exceptionally low disorder two-dimensional electron system. So as an example, one can study these materials in a large magnetic field. And if you study a two-dimensional system in a large magnetic field, the band structure you probably solved in quantum mechanics is described by Landau levels, which are very highly degenerate bands that have zero bandwidth. And the way to think about this is that everywhere in the sample, classically an electron is undergoing cyclotron motion. That cyclotron motion is quantized. And so everywhere in the sample, the energy is effectively the same. So there are very degenerate levels. That degeneracy is going to be lifted by disorder, meaning that in different parts of the sample, you will have different potentials. And as a result, all of the bandwidth in a Landau level comes from disorder. So they're an excellent probe of disorder in your sample, because if you have a lot of disorder, you're going to see Landau levels that basically don't do anything. But if you have very little disorder, when you partially fill the Landau level, you'll get a whole sequence of different correlated electron states where that degeneracy is lifted by Coulomb interactions. So this is fractional quantum Hall effect, Nobel Prize in 1998, and of course, just a wealth of physics over the last 40 years at this point. And if you study these types of systems, so this is graphite gated hexagonal boron nitride dielectric bilayer graphene, you see this huge, this sequence of fractional quantum Hall states that basically, sparing you the details, indicate that these samples are really exceptionally clean, as clean or cleaner than what you can realize in, with molecular beam epitaxy grown semiconductors, for example. Okay, and what I'm showing here, just a preview, that what you're, the way you can operate these devices is you have gate electrodes that are made of graphite, but they're connected to voltage sources, and you can tune that electric field as well as the density through the sum and difference of these top and bottom gate voltages. Okay, so if we want to study this rhombohedral graphene, actually we owe a debt to Feng Wang, who sort of gave us some pointers in the early days of doing these experiments. You need to isolate these ABC trilayer flakes. You need to prevent them from relaxing to their ground state, which basically you accomplish by being relatively careful, and there's a process that you can develop. But one of the sort of advantages here is that this studying these rhombohedral layers and as well as the Bernal layers, there's no particular reason why you should have any disorder. We know that the disorder can be very low in our intrinsically in our fabrication process, but for these rhombohedral layers, they tend to fail completely or not fail at all, and that's that basically allows you to have large single domains of this rhombohedral trilayer graphene. The measurements I'm going to show you at the beginning are inverse compressibility. So compressibility measures basically the energy cost of adding charge to a two-dimensional electron system, right? So the change in chemical potential induced by changing the density. The way we measure that is capacitively. And just to give an idea of what data may look like, this is that experiment done in the quantum Hall regime. And what you see is that there are, as a function of the density, which is along this axis, every time there's an insulating state, you see penetration of the electric field from this bottom graphite to the top graphite, and you see a little peak. And then near those insulating states, you see it go slightly negative. That's because you have some correlations that lower its energy as compared to a uniform sheet of metal. But this is basically the experiment I'm going to show you. Okay, so to just show you some basic, the basic data in rhombohedral trilayer graphene, what I'm showing you here is a color plot of this inverse compressibility plotted as a function of density and the electric field applied across the layers. Okay, so this displacement field is the electric field applied across the layers. And what I will ask you to believe without proof is that if you do a calculation of what the single particle quantum mechanics of this ABC trilayer says the electronic compressibility should be, you will find essentially none of the features. I'm sorry, the contrast is not rendering well on this projector, but there's sort of one feature out here that's a single particle feature, but everything else basically is not in the single particle model. And in particular, it's obvious to see why that might be, because there are a number of features here where the compressibility is strongly negative. So you can see these bright blue lines around. And that's, of course, basically saying there's negative density of states, which is not something that will ever occur in a single particle model, but is something that we know from many experiments, and you can show relatively simply, is associated with first order phase transitions where the density changes suddenly, right? So what we're seeing here is as a function of the density, as you lower the density, here's for electron doping and for hole doping, as you lower the density, the system goes through a series of first order phase transitions between phases that are apparently distinct. And what I'm going to show you is that all of these phases are essentially different types of ferromagnets corresponding to ordering of the spins or the valleys in this system, right? And as might make sense from the discussion before and from this band structure, you see that all of this physics gets stronger and emerges as you apply this electric field and make that spike in density of states go up. So what's plotted here is the non-interacting band structure at zero displacement field, where there's sort of small increases in density of states, and then as at large displacement field, you get these very big spikes. Okay. So to give an example of how we can try to probe what's going on here, there's a technique that's very common in condensed matter physics, which is to look at the response of a system's transport to small out-of-plane magnetic fields. And what this causes the electrons to do, small magnetic fields, is to undergo cyclotron motion. And the quantum interference, and think about the quantum interference of an electron trajectory coming back and impinging, let's say, on the same impurity, there'll be constructive and destructive interferences. And it turns out that though the interference condition for a quantum oscillation precisely tells you the area of the Fermi surface in momentum space. Okay, so it's a way of mapping out the Fermi surfaces, and this is a very old technique. It goes back to the 1930s. It's how people first figured out the shape of the Fermi surface of copper was by doing so-called Shubnikov de Haas or de Haas von Alphen. Usually de Haas's name came up, but he was the one who sort of first started doing this. So if we do quantum oscillation measurements in each of these regimes, what I'll show you here is actually a plot of the Fourier transform of these oscillations, but plotted in particular units, where the x-axis, which I'll call f nu, is the area of the Fermi surface normalized by the total density of electrons. So what does that mean? It means basically that if I have a peak at a quarter, which is what I get at high density, that basically means that one trajectory around the Fermi surface covers a quarter of the total electron density. And that's exactly what you generally expect in graphene systems, because you have four flavors. You have spins and you have valleys. There's two of each. You have four different ways you can put electrons into the system. And so each one of those, if there's nothing interesting going on, will give you a quarter of the electron density per flavor. Just like in a normal system, you might have a spin up and spin down. And so you'll have half of the population in spin up and half in spin down. In graphene, it's a quarter. But as we lower the density and cross these transitions, you go to a half and then finally one. That's basically saying that you now have a metal that only has half of the degrees of freedom, and then finally one that only has a quarter. In other words, the electrons have just gone into the system and chosen to all spontaneously polarize onto one of the spins and valleys. Okay, maybe I'll skip this, but it turns out that you can actually go and understand exactly which of these degrees of freedom are being occupied under certain circumstances by looking at things like their dependence on in-plane fields, which tune the spin alone, and their transport properties, which tell you about the total Berry curve, which I'll come back to. So you can understand that you have, a half metal, for example, something that just has one spin projection and has both valleys equally occupied, or at the lowest density is actually a quarter metal that's spin and valley polarized, where effectively the electrons have just decided to condense into one corner of momentum space, and it's really an orbital magnet. Okay, it turns out we can actually look at this, in a bit more detail. So let me introduce sort of a different technique, right, which is nanosquid on tip microscopy. So if we'd like to be able to understand these magnets microscopically and understand really what they look like in our devices, and that turns out to be difficult because these are very small total magnetic moments. So if you just estimate, how much fringe magnetic field, for example, you expect from these very low densities of electrons, you find, that it's equivalent to something like 100 nanotesla of magnetic field, which is rather challenging to to detect on scales of sub-micron, few hundred nanometers, the general scale that they're of our devices. So to do this, we basically built in my lab over the last few years this technique originally developed by Eli Zeldov at Weizmann Institute, where you can fabricate a squid, a DC squid, on the tip of a very sharp quartz needle. So you basically pull a quartz tube to a very small diameter. Here, there's something on the order of a couple hundred nanometers, but you can make these as small as 30 nanometers or 40 nanometers. And by evaporating superconductor on both sides, you end up with 2 weak-link Josephson junctions at the corners and basically a squid. So you can see here, this is the voltage across that squid modulated by the applied magnetic field. And if you make these tips the right way, you can get diameters, let's say, and the ones we'll be using are in the 1 to 200 nanometer range, and they have magnetic field noise of on the order of 15 nanotesla per root hertz, which is extremely small, and it allows you to resolve these very small fringe magnetic fields from these magnetic states. And we've built this in our lab in a couple of different systems operating at 1.5 Kelvin, or the data I'll show you is mostly from recently qualified 300 millikelvin system. So, oh, sorry, yeah. So this is an SEM micrograph of a tip, and this is that tip. This is the quartz tube. Okay, and that quartz tube, that's the tip, is up there, and what's smashing into it is a quartz tuning fork from a wristwatch, like a digital wristwatch, and you can actually use that to do topographic feedback, because that'll vibrate at 32 kilohertz, and then you can use that to touch the surface and figure out where you are and prevent yourself from smashing your tip. The downside of these tips is that they have this tiny thin film of like 15 nanometers of superconductor on the end, and it's just not very hard to destroy that. And yet you need to find where you are, and so this is a way to navigate. It's sort of a technical thing. You can also use it to spatially modulate the tip and do gradient magnetometry, which I'll show you a bit later. But for now, anyway, it's just a navigation tool. But this is what the tips look like as they're loaded into the microscope. Okay, so the imaging I'm going to show you is actually, so here's a sort of schematic of what a device might look like, right? You have a graphite gate, you have hexagonal boron nitride gate dielectrics, you have a layer of interest. And one of the nice things about this technique is that because you're doing magnetic imaging, you can see right through your electrostatic gate. So there's no interaction between the tip and the sample that's not magnetic. There's no electrical interaction, which is kind of helpful. And then what we're going to measure here is we need to be able to modulate our signal at some frequency that's above the 1/f noise of our system. So we're going to modulate the bottom gate. And modulating the bottom gate, we're going to be able to look at when there are changes in the fringe magnetic fields of our sample by then taking our tip and scanning it around or sitting it in a spot and looking at how that dB/dVg signal changes as a function of the density. Okay, so what we're going to go to our ABC trilayer graphene sample, and here was the capacitance data I showed you. We're going to go over to this regime here where there's a kind of quarter metal state and a half metal state, and zoom in to a region like this. And we're just going to sit somewhere in the corner of the sample where we expect to see a nice fringe magnetic field. And this is basically what the data looks like. So indeed, we see magnetic fields from this tiny piece of graphene. And you can actually see 2 transitions here. This turns out to be a spin polarization transition. So it's at higher density. And what you're seeing here is basically the fact that as you tune the density, there's a region where there's a first order transition from being spin unpolarized to spin polarized. So the fringe magnetic field suddenly turns on, and you see that sudden turn on because there's a step and you see a little peak that comes from turning on the spin polarization. But then as you reduce the density further, you see a much bigger spike that happens where you have a really big, by our standards anyway, it's 100 nanotesla signal at a much lower density. And what that comes from is that you now have gone from having your electrons in both valleys to suddenly having them all in one valley. And that momentum space condensation comes with a large orbital moment, right? And this is where you polarize into wave functions that have a large orbital moment. And the signal is bigger because that orbital moment is much larger than the spin magnetization. So now you can map out the sample. So here's our little Dorito-shaped rhombohedral trilayer graphite flake. This is imaged by sitting along this orbital transition and then scanning the tip around. And you can see that it's, relatively uniform. And those of you who are in this business will recognize these as little bubbles of, some contamination, but otherwise the magnetization seems relatively uniform. This is what you expect if you have a uniform out of plane magnetization, is to see actually a fair amount of magnetic field, uniformly over the bulk from essentially finite size effects. Okay, and the key point that I want to just emphasize is that this magnetization is basically all orbital. Everything if this were purely a spin magnet, this signal would be essentially below our detection sensitivity. It's much smaller. Okay, and the way to understand where this comes from in graphene actually was pointed out, just very shortly after the original experimental discovery of graphene. It's that which happened to come, just on the heels of what people would call the modern theory of orbital magnetization, which is that if you think about how to project the angular momentum operator into the block states that are in a solid and work that out carefully, you get a formula that looks something like this. And this was all developed by Shan Nu largely, and where I lifted this formula from. There's a nice review paper. There's an orbital magnetization that arises from the bulk wave functions. And in graphene, that this consists of really two sort of distinct contributions. You can think about it as the wave packets formed of the block states have a self-rotation part, and then they have a kind of a center of mass motion. And the wave packet self-rotation part is sort of a bulk magnetization, and then the center of mass motion is something that essentially is, can lead to edge states, as I'll discuss a little bit later. But this all comes basically from thinking about what does angular momentum look like for block waves. And the key insight is that in graphene, without any symmetry breaking, there's no orbital magnetization. But if you just open up a gap at these Dirac points, you always generate some orbital magnetization. On the other hand, orbital magnetization, of course, like any magnetization, has to vanish if you have time reversal symmetry breaking. And the way this works out in graphene is that the different valleys, once you introduce a band gap, which can happen any number of ways, in the systems I'm telling you about, it comes from the electric field, there's an equal and opposite polarization in the different valleys. Okay, but what's happening in this system, and the signals that I'm showing you effectively come from the fact that once you have ferromagnetic polarization where all of the electrons join this one valley, then this polarization becomes very large, and you see that magnetization, which really is just coming from the electrons, if you want to think about it in real space, undergoing some kind of orbital motion. And that's just the vast majority of the magnetization in this system. Okay, it behaves in many ways like a clean magnet. So we can look at, for example, the dependence on magnetic field, where we can tune the magnetic field, up and down, and you can see that it'll hysteretically switch. And it turns out it switches very cleanly. There's just a single domain that will propagate throughout the whole sample. There's no Barkhausen noise, for those of you who are familiar with that. And that's just because the orbital moment, like any other magnetic moment, couples to the magnetic field, right? And it's just switching the valleys, from one valley to the other as you switch the magnetic field. Turns out you can also switch that with an electric field, because these transitions are so first order and so metastable that you can just tune a gate voltage, in this case the displacement field, between a paramagnetic state and a ferromagnetic state, and see hysteretic switching between a paramagnetic state and a ferromagnetic state, which is not entirely, it's sort of relatively difficult to realize that in most 2D magnetic systems. It's sort of a signature of there being a relatively clean system. Okay, something that I won't be able to talk about, but I just will mention, is that, in this talk, is that, all of these magnetic states are also associated with superconductivity, right? So along the borders of many of these magnetic transitions, there's actually a whole variety of superconductors that arise, singlet and also spin triplet. In rhombohedral trilayer graphene, and also more recently in just absolutely conventional Bernal bilayer graphene, so a system that has been studied 10,000 times, and it turns out also superconducts for sufficiently low temperatures, and unexpectedly only with the application of a large in-plane magnetic field. And it seems there's a spin triplet superconductor that has been sort of sitting there the whole time. And it seems likely that the superconductivity is associated with magnetic fluctuations, but it's very hard to prove that, as I think everybody who's worked on unconventional superconductors knows. It's a hard thing to pin down, even with all of the tunability that you have in these systems. Anyway, subject of ongoing work and the subject of perhaps a different talk. So instead, I want to sort of shift gears a little bit and talk about what else you can do. In particular, what I've told you about so far is really all about the physics of metals, right? So talk about Stoner, ferromagnetism, and a little bit superconductivity. That's all the physics of metals. And one would like to realize also the physics of insulating states, because there are many things that are nice about insulating states. Things are quantized in insulating states. They're actually good quantum numbers, whereas in metal, they typically are not. And to do this, it's rather difficult. You sort of need to be at some commensurate filling of the bands. And in the systems I've shown you so far, which are basically just graphite, you really only have one choice, which is charge neutrality, which is not where you have the large density of states, even in these other systems. So it turns out that the elegant solution to that is a superlattice potential, which allows you to have a much larger superlattice wavelength, where you can then go to integer or fractional filling of that superlattice and realize integer or fractional states. So one example, from a local example from Berkeley is ABC with a moire, which actually predated all this work, but that I've shown you so far, where you just take ABC and put it aligned to a hexagonal boron nitride crystal. Hexagonal boron, if you align them, there's a lattice mismatch, and that generates a superlattice potential. And then what Feng Wang and collaborators observed is that you get insulating or at least resistive states at various commensurate fillings of that superlattice potential. So here at a quarter filling, which I would call nu equals 1 electron per superlattice unit cell, 2 electrons per superlattice unit cell, you find these resistive states. And that's something that basically happens if you break these spin and valley symmetries, then you can have insulating states on the lattice. And I would say now we understand that reasonably well, as the ferromagnetism I showed you, plus some weak periodic potential from the underlying HBN substrate, can allow you to have these states as very, very sort of natural. Another famous example is twisted bilayer graphene, where you have a moire potential from rotating two graphene monolayers. There, the mechanism for generating the correlations is slightly different, because it's that twisting at some resonance between the interlayer tunneling and that twist angle that generates a high density of states near charge neutrality in a flat band. But the physics is basically similar otherwise, in that you have now large density of states, and as a result, you have all of these correlation effects that can break the symmetry. So you can make this flat band when you get close to 1.1 degrees, and then you see correlated insulators again at fractional filling of that band, superconductivity, and also magnetism, just like in the systems that I showed you. So just to give an example of what can happen when you have this intersection of magnetism and now flat band physics and a moire potential, here's an experiment from twisted bilayer graphene aligned to hexagonal boron nitride for those who are interested in the details. And you see that there's indeed magnetic hysteresis, in this case at 3 electrons per unit cell, but remarkably, the Hall effect here is perfectly quantized, and you see vanishing resistivity at zero, at zero magnetic field. So you have this combination of Rxy of h over e squared, just the resistance quantum, and Rxx of 0. Okay, and there was a similar experiment around the same time, also from the Berkeley Fudan collaboration on ABC on hexagonal boron nitride, saw something similar. Right? So how to understand this? This is exactly a quantum anomalous Hall effect. It's what can happen when you have broken time reversal symmetry and large Berry curvature and finite Chern numbers, which I'll describe in a second, in an insulating state. So the idea is that with quantum Hall effect, you have high magnetic fields, low temperatures, and you end up with these dissipationless chiral edge states. And their signature is precisely Rxy being quantized in units of this conductance quantum and Rxx vanishing. It was proposed already by Haldane in the 80s that it should be possible to do this without a physical magnetic field. The particular realization that he envisioned was kind of complicated to realize in experiment, but essentially amounts to having some broken time reversal symmetry, but no net flux effectively, right? And the excitement about this type of state of matter comes from the fact that while the physics of Landau levels is ultimately limited to sort of a low temperature physics, because it's just, in principle, you can make an infinitely large magnetic field and get an infinitely large temperature, but magnetic field is a very expensive knob to turn. The cost of a magnet goes up very rapidly as you go to larger magnetic fields. And indeed, the largest static magnetic fields are sort of in the world after, this is like tens of years of development, still like 45 Tesla. Maybe they can get to 60 Tesla, but that's only actually a few times bigger than, what you can get in a lab. And it's just hard, that's not something that's going to increase anytime soon. On the other hand, magnetism, realizing this type of effect with pure magnetism, we all have refrigerator magnets. It's possible to make magnetism a room temperature effect. And there are various uses for these types of things that people have imagined, most prosaically resistance metrology, but maybe, microwave circulators, doing all kinds of other dissipationless interconnects, topological qubits with the right combination and so on. And this effect was realized actually in a totally different set of systems in 2013 using, magnetic doping of thin films with strong spin orbit coupling. And they basically saw a quantized effect, but only emerging at very low temperatures, 50 millikelvin, in a rather disordered limit. So actually the effect that I'm showing you here is something observed easily at a couple of Kelvin and actually survives up to 4 or 5 Kelvin with good quantization. So there's sort of a different energy scale going on. So to understand what's going on, right, actually we can just go back to this formula for the orbital magnetization, and we see that the same effect that generates the orbital magnetization, the Berry curvature, right, is the same thing responsible for quantization of the Hall effect. So if you, it's famously proven by Thales and collaborators, the quantized Hall effect, you can think about it as a sum of the Chern numbers, which is our topological invariant of filled bands, over all the occupied bands. And it turns out that that Chern number is simply the integral of exactly this same Berry curvature over these filled bands. So the same incipient Berry curvature that gets generated when you gap out monolayer graphene is responsible for then giving these bands, some finite Chern numbers, and that's something that happens. The contrast is really not great. In twisted bilayer graphene, where all of these flat bands have some finite Chern number. Okay, so we understand this Chern, the presence of these quantized anomalous Hall insulators in these graphene systems reasonably well from this sort of single particle plus polarizing into these bands. You have to break time reversal symmetry and so on, but we already know that that can happen. I want to just in the last bit of the talk about an interesting consequence of this compared to conventional. Was that a question or? Okay, just. Oh, that's the Berry curvature, or the Berry connection. So I want to point out one, kind of cool thing that that emerges from this. So let's think about what happens when you're in one of these Chern insulator gaps. So this is a formula for the magnetization owing to these orbital states. Okay, if you're in a gap, then it means that you are not changing the occupation of any states in the bulk because there are no bulk states. Okay, so this first wave packet self-rotation term is not changing because you're not changing the occupied states in the bulk. And this term is also not changing, but the chemical potential is indeed changing inside the gap. And basically what that means is that inside a gap, the magnetization simply scales with the chemical potential and the Chern number, the gap, and this is just the magnetic flux one. The way to understand that is simply that as you tune the chemical potential through a gap, you have edge states at the boundary, and those edge states have angular momentum. They have a magnetization. They're not really distinct from a bulk magnetization from the point of view of a measurement, but they're there even inside the gap. Now, this is a very small effect in, for example, a quantum anomalous Hall effect in a magnetically doped Chern insulator, because there's a huge magnetization from the spins, right? Those systems, as an example, they're full of chromium atoms, which have the local moments, and there's 3 orders of magnitude more local moments than there is a magnetization from these edge states. On the other hand, in these purely orbital magnets, basically this is the entire magnetization. So you can compare the magnetization of the filled bands to the magnetization of this edge state. And it turns out they're generally speaking going to be the same size. And what's kind of, turns out to be remarkable is they can be the same size, but they don't have to be the same sign. And in fact, generally they're not the same sign. So what that means is that the magnetization of the edge states alone can be as big as the magnetization of all the bulk states. And what that means again is that if it's bigger and the wrong sign, then as you fill those edge states, it can turn out that you just go from being in the ground state to not being in the ground state. So let me illustrate what that means and what that allows you to do. So here's, to do that, I have to change some details. You had to sort of swim around in this space of different layers you can twist on top of each other to find the right experimental system where this can work. It turns out it works in a system called twisted, it's a monolayer twisted on a bilayer. Turns out to be the sort of right system to do this. And what I'm plotting here is just transport. This is resistivity as a function of density and displacement field. And there's a particular regime of densities and displacement fields and twist angles where you have some features at 1, 2, or 3 electrons per moire unit cell. And it turns out if you look at these closely, you'll see that they have nearly vanishing longitudinal resistivity and nearly quantized or quantized Hall resistance with a Chern number of 2, it turns out, and that's something that we understand reasonably well. But there's something sort of special that happens here at 3 electrons per unit cell, which when I first saw the data coming out, I thought, for sure there's a broken wire in our cryostat, for sure there's a broken preamp, and why is this switching around it? So what's being plotted here on a color scale is actually the Hall resistance, and the way this data was taken is that the density is rastered on the fast axis, and we ramp the magnetic field on the slow axis, so you're ramping back and forth, and what you see that's surprising, or should be surprising, is that the sign of the Hall effect is actually flipping back and forth as you sweep the charge carrier density. That's, and very rapidly, there's like a very sharp change. It really looks like a broken wire, some intermittent connection or something like that. And I, told my, postdoc at the time that this was definitely wrong and that, we should check that all the wires are connected and so on. And he said, no, and it's real. And we went back and forth on this a little while. And it turns out that it is indeed real and that it comes from precisely this effect. So what I'm showing here in a 3D plot is a much more carefully taken data where on this axis is the magnetic field. And what you can see is that you can switch between quantized Hall effects as a function of magnetic field, which makes sense. You have orbital moments and you couple to them with a magnetic field. And as you change the magnetic field, you couple to the K valley or you couple to the K prime valley, and you can switch back and forth, and there's metastable dynamics. So you stay in one and you get hysteretic switching between these two. Makes sense. The whole system has an orbital moment and you just couple to that with the magnetic field. But you also see hysteretic switching along the axis of really the applied voltage to the gates. Okay, so it switches between again, like a positive and negative quantized Hall effect. And the way we understand this, and there was a theory paper from Alan McDonald's group at just the right time, actually sort of half predicting, half post-predicting this effect, is that in fact, what's happening is that in the gap, all you're doing is changing the population of the edge states, but somewhere in the gap, you go from having a net positive magnetization in one valley to the magnetization switching sign to being negative. So all you've done is change the occupied states just in this edge state, and you've gone from the K valley having positive magnetization to the K valley having negative magnetization. Now, what this means is if you have a small magnetic field, you were in the K valley and it was aligned with the magnetic field, you've now changed the carrier density, really just the density of electrons in this topological edge state, and it's gone from being in the ground state to now suddenly being in the wrong state, right? It's switched the magnetic moment by microscopic tuning just of which wave functions are occupied in your sample. And now you find yourself in the wrong state. Now you still have some metastability, so you survive there for a little while until now the electronic system relaxes to the other valley. But this is entirely tuned by an electric field, and you're switching the magnetization basically up and down with an electric field. So if you want to sort of push this, what you can do is then go through a series of pulses in magnetic field where you can obviously do hysteretic switching, just like you would in a normal ferromagnet, but then you can also make little switches on this voltage axis and just do this exact same thing. So what's shown here is sort of a bunch of ramps of magnetic field and a bunch of ramps of a voltage on a gate, and you can see that you can accomplish the same non-volatile switching of your one world's most expensive magnetic bit using either a magnetic field or a gate voltage. Anyway, to finish, let me just give you a slight outlook of where I think we can improve things. So I showed you this image before of ABC trilayer. This is a system without a moire, and it's very uniform with the exception of these sort of known and preventable fabrication defects. It's uniform over many microns. Basically, the magnetization looks the same. If we do comparable magnetic imaging of these moire systems like twisted bilayer, twisted monobi, they're actually extremely non-uniform and extremely disordered. And this has been a major limitation. So actually that quantized anomalous Hall that I showed you, we basically, in twisted bilayer graphene, we've never been able to reproduce. That was absolutely just like a one device that worked, and every other device, some detail is not the same, right? Monobi is a little bit better, but still the quantitative details are always different. So these types of moire systems are hard. The reason for that is that twisted bilayer graphene is not, it's at magic angle, it's magic for the electronic structure, but it's not magic for the structure. It's a metastable, it's not even a metastable state, it's simply unstable. So you're quenching in whatever disorder there is when you make it, and it's just very hard to do that in a way that's perfect. You can't rely on any kinetics to help you. They're just your enemy, right? And so this is sort of, generically you get very disordered magnetic structure, and you can do many other types of imaging and see that it's just all over the place most of the time. So on the other hand, without a moire, you don't get these insulating states. You don't get quantized physics of insulators at finite density, which you would very much like, because that's what allows you to, to play all kinds of enjoyable games. So how to do better, right? So actually the answer, I think, is heterobilayers. These mean moires that are generated much like the ABC HBN of layers that have different lattice constants, right? And so just to give an example, there was this beautiful result just last year from Kinfei Mak and Ji Shan's group in heterobilayer of transition metal chalcogenides. This is a stack of tungsten selenide and molybdenum ditelluride. These are two systems that have slightly different lattice constants. And it turns out that for the right choice of electric fields, you get a quantized anomalous Hall effect again at one hole per unit cell. And so we can do imaging on that structure. Actually, this image here is taken on that, and I sort of cheated and stole this figure rather than remaking it earlier in the talk. And you can see, that there's certainly structure, but we can look at that relatively carefully. And what we see is that there's, there's plenty of defects, right? There are plenty of the same sort of bubbles, but there are large ranges, over many microns where there's uniform magnetization. So this looks much more promising from the point of view of being able to realize low disorder moire structures. You kind of have a correlation length for the twist angle, let's say, that is 5 microns rather than 200 nanometers. And that's very helpful. And anyway, there's still lots of work to be done, but that's kind of, the direction that I think, we're slowly going in the material science of these systems to try and find, better moires, places where you can now get to, more sharply into strong correlation limits. And there's a wealth of other more subtle correlation physics, both of superconductivity, and the Hubbard model, and Wigner crystals and other states at fractional filling that I didn't get into, but that you can realize under these different circumstances. So anyway, with that, let me conclude. I hope that gave you a taste of some of what we've been working on, and thank in particular, all of the students in my research group, but in particular, Hausch and Zhou, who really kind of broke through the logjam of understanding these non-moire systems, and Charlie Cheerhart, Marek Serlin, and Gregory Polshin, who led the magnetism in moire systems that I showed. So thanks to all of you. Take the question.
So what breaks the very inset?
Oh, because there's a small magnetic field. Yeah, there's a small magnetic field applied, and you're switching which valley moment is aligned with the magnetic field. Yeah. So basically, you think about it, it's going sort of like, as a function of gate voltage, the field points this way, and the moments are going like that. So you go from being in this one, and then as you switch them, then it jumps to this one. Yeah, that's a great question, right? I think that, there is a major, okay, there's a question of where's the field going. There's a question where I'm going. Let me answer the question of where the field is going, and maybe not answer the question where I'm going personally, because it might be just not to continue this, right? But I think that in the, there's a major issue with manufacturing of these things. Like, is any of this going to be useful I think that without a breakthrough in how to make these things at some kind of scale, none of this is going to be commodity electronics. That's just ridiculous, right? There's no particular hope of that. Can you understand better certain models? Sure, yeah, that type of physics will continue for a while. I think other work from Kin-Fai Mak and Ji Shen recently on realizing the Hubbard model is sort of a breakthrough for people who are interested in that. For me personally, I think that things I didn't show you too much are that we are able now to make these systems, these two-dimensional systems that are really quite perfect, more perfect than any just simple two-dimensional system that was made before. So there's a wealth of physics to do at the intersection of many body physics and quantum information that I think is really exciting. Things that maybe people proposed in the 90s or 2000s that I think now are going to be just straightforward to do because of the technical developments that in many cases were developed in order to study this kind of physics for fun, has turned out to allow us to do fractional quantum Hall experiments that were never possible to do in gallium arsenide. Maybe we'll make a topological qubit out of it. I think that will actually work now because of the material science developments that have come out of that. So that's where we're going for the most part. And then the question of whether, yeah, I think it's hard to go the commodity electronics direction, stacking things like that. You need growth to cooperate, and I just don't think it has for 2D materials. So. So homo bilayers, if there's a, you definitely want to avoid magic angle conditions, right? Even if there's no magic angle condition, homo bilayers are always going to be probably more stable at 0 angle, in which case they're not really a moire. So I would like, and we try to avoid now studying things that rely on us getting a uniform angle without relying on some amount of structural stability. Like you'd like to be able to cook your sample and have it get better rather than cook it to have the effect go away. And if you anneal a sample that's at an angle and it goes to 0 and your physics goes away, that's bad. If you anneal your sample and it goes to 0 and your physics gets more uniform, then that's good. So hetero bilayers are good, homo bilayers bad. That's sort of the mantra, I think, now for us. So the thing that worked here is don't have any spin magnetization. That's good, right? So no spin orbit coupling is useful. And then large Berry curvature, right? And then you'll get a big orbital magnetization, and if you don't have much spin orbit, then the spins are not really going to order by themselves. Well, we've thought about that. Like in a hero experiment, maybe you'd be able to do some NMR, which would be fun. I don't think too much should change in this physics, but we've thought about that mostly from the point of view of two things. One is whether you could actually use that to do NMR, and that turns out to be pretty marginal because the pi orbitals just don't have much hyperfine, and probably the numbers don't work out. The other thing you could try to do is the isotope effect. So one idea that we had was to make Bernal bilayers that had carbon-13 and carbon-12, and then you put the electric field on one side and put the electric field on the other and see if you could see an isotope effect. But given current TCs, that would be looking for like a sub-millikelvin, like a quarter of a millikelvin change in TC, which is anyway tunable by gates. And the samples are quite reproducible now, but not at a level of 250 microkelvin TC. So there are other things that would change. So those are the sort of two ideas we've had. I don't think the isotope effects, it's a 1% effect for square root of whatever, 13 over 12. Yeah, I don't know. It's kind of weak, I think, is the short answer. Thanks, Mike. Thanks, everybody.